Okay, I think we left off with this one. Uh, Somehow, I guess it was in a different presentation. We did something about a sequence detector, but that's what this is too. This is a different kind of sequence detector. Okay. Uh, this is another just type of problem. If we can get into it today, I don't think we'll get into it today, but if we can, uh, I'll I'll skip this one because we already did this one, didn't we? Alternate FSM design approaches. Somehow I missed. Uh, yeah, we did this one, but somehow I missed this example design, and I was going to skip that to later anyway and go into vending machine. So we'll see what happens. If we can get this all the way done today, uh, then we'll go into the vending machine. Okay, this one this is a design description to implement another type of sequence detector. This one has an input of W and output of Z. If the output will go high if the two previous values of W were both 0 or were both 1. So that's a little different than the last one we had. Otherwise, the output will be low. So in this one, I said, okay, there we've got that. So we had to derive the state machine and develop the diagram. And I did this one as I did the diagram. Now I might have made a few changes in this as I went along. So this was my last uh, attempt at this, not my first. Okay, because I may have changed it a few times. So I said, okay, I'll start with this. I'm always starting with some kind of reset, so I may as well put it in there to begin with and say that that's going to start with state A. The next state, I know this one's 0, the output 0, and again, it looks like I'm starting with a Moore machine because I'm associating this output with the state. But because there's been no pulses as of yet, we may as well say the output is Z, or a 0. So I can go two ways here. I can say that the first or the first pulse I got, the first value on W was 0, or the first value on W was 1. Either way, that's only 1 0 or 1 1. And then in both cases, Z would be 0. Now, see, this may not be the way I would have started to begin with, but after I got further into it, I realized, yeah, I probably need to do it this way. Okay, so I added this branch, a new, and that's why I have ABD. You can tell this is my last attempt, not my first. Here's C. It said W is equal to 0. Well, if W was 0 twice in a row, then my output was supposed to go high. So again, the output's associated with a state. In that case, it's C. But if it was low and then it went high, well, I wasn't in state C. I was over here. So you can think of state D as being that state that has just that W's been one time. And state B is when W has been 0 one time. State C is when it's been 0 two times. So there's probably a D, there's probably an E down here. Oh, if it keeps doing 0, then we just keep Z high and stay there. If it ever goes back to 1, though, we keep going back to D, where this is that state that says W has gone high once. Then if W has gone high a second time, we're in a new state, and Z is high again, and uh, we got some other things to add in here, but at least we're taking care of that one. Then, if we're in D, and it's been high, W's been high once, but now it's a 0, we need to go back to B. That's the case where there's been 1, 0. If we've had W 1 twice, and here it's still a 1, then we stay in E and we keep making the output high. And then this one is if ever we were in state E where we had two 1s and then got another 0, we'd have to go back to B. And again, B is that state that says there's only been 1, 0. Okay. Does that make some sort of sense? I mean, no, yes, but yeah, this is a different kind of a problem, having 2 zeros or 2 1s in a row. And like I said, there may have been many different ways of setting this up, but that was my last attempt. My first one, I crumbled up and threw away. I think my second and third and fourth one, I crumbled up and threw away. And then I came up with this one. So I've said before that you're probably going to have a sequence detector on the final. Let's hope it's not this one, right? Or something harder than this one, right? Something easier than this one, more like the last one that we had. But we don't know, do we? I mean, I haven't seen the final yet. I've seen it, but I can't remember it. So you guys haven't seen it yet, have you? Huh? You can put it up there. We'll see it. No, I won't put it up there. Let's check it out. Okay, so from this, I should actually what I should do. It says develop the state table. Okay, well we should do that, but if we can, we might be able to go straight to the VHDL from that. Some of you can do that. I mean, I can do this if I wanted to. Sometimes I like going from the state table. So what I usually do is say in my steps that we go ahead and should develop a state table. And after we do that, then we can decide on the number of variables and start going from there, implementing the design. Now, if we've got A, B, C, D, E, we got 5 states here, 2 inputs, or I'm sorry, 1 input, 1 output. How many state variables are we going to have? Minimum. What's the minimum number of state variables? Or, you know, QA, QB, QC, the outputs on flip-flops. I'm not saying they're D or RS or JK or T. I'm just saying, how many do we need? Well, we know it's going to be more than 1 would take care of 2 states. 2 would take care of 4 of these states, and unfortunately we have 5, so we would need to have at least 3. Okay, so from my state table, I decided we had 1, 2, 3, 4, 5 states. We'd end up having 5 state variables here. So here I'm trying to show how to draw or how to design the state table based on this state diagram. So here we are, state A. That's my present state. The output is associated with the present state. Possible inputs are 0 and W, or 0 and 1 for W. If the input was 0, then I would go to state B, right? If my input was 1, I would go to state D. Now, I'm not saying anything about the outputs here because the outputs are associated with the current input uh, or the current state. So we got to go to that state before we start writing anything about the outputs. But at least we've got state A, a transition, and this output taken care of. Okay, here we're in state B. That's our current state. Again, W could be a 0 or a 1. Associated with state B is the output of 0. If W is a 0, where am I going to go? I'm going to go to C. If W is, I'm sorry, a 1, so I'm in here, I'm in B. If W is a 1, I'm going to go to D again. Okay, shows that. Either way, output 0. C, we got state C, that's here, output's a 1. W can be 0 or 1. We can get to stay at state C or move over to state D. That's what this one's showing. Okay, I thought somewhere in here we just completed the table. So normally I would say here, have a little quiz and complete the state table. But what I'm going to do is that and just complete it and keep moving. Okay, so if we're in state D, that's our current state. Our output's a 0. We can see if W is a 0, we go back to B. That's showing. If W is a 1, we go over to E. And then E, if state or W is a 0, we go back to B. And if it's a 1, we stay in E. Output's 1. That's what it says here. Does that help at all? I mean, having this state table, does that help that mind-blowing type stuff at the beginning? That final exam, I mean, I can't remember. I think I've had about 5 or 6 different types, but there was a sequence detector on each one of them, and it was a lot of fun. Now remember, for every version I got, I had to go through it myself too, and go through the design to make sure you guys did it right. But on every one of those, I then put it in Xilinx, created a test bench, and made sure that the answers I was getting were correct. Okay, so I did that. We know that we're going to need 3 state variables, right? So if here we should also be saying if we're going to just do Xilinx, if we're going to create a VHDL file for either that or some other complex programmable logic device, then we can really skip step 4 and 5. We could just go to implement the design right from here. I think you guys can do that, can't you? You don't need the rest of it. This is all you really need if you're going to go to VHDL from this point. I like this, I think, depending. This gets a little confusing. There's too many arrows going every different way and too many variables. Maybe it would help if z equals 0 was inside that circle. Okay. So if we were going to do that, we would just skip that. We're still going to do both, but we're going to start with VHDL in this case. So let's go and look at what our inputs are going to have to be. I'm almost all, well, for any state machine, unless you're going to make it an asynchronous machine, which I think something that's going to blow your mind would be an asynchronous machine. So we're going to we're making synchronous, so we're going to have a clock input. We're going to need reset input. Now the book that I saw this example in, again, I've used several examples out of this book. I can't remember which one it was, but it always says reset N. I don't know why, but that's where that reset N comes from. And then the input W, they're all just an input standard logic. We have one output, and that's Z. Okay? Then, let me go back. So we've got all our inputs and outputs here. We normally do this a little different. I did it this way to keep it all on one page. Uh, Again, I'm doing a state diagram or a state uh, description of a state machine. So I almost always create a type that's a state type, and I almost always will name some kind of signal or create some kind of signal, give it a variable name, and then tell it that it's a state type. But that gives me five flip-flops, and but if I were going to put Q out here, and I'm not doing that this time. This time I don't care about the output of the flip-flops. We have up until now, but this time I don't care about that. All I care about is when is Z going to be 0 and when is Z going to be 1. Well, Z will be a 1 when we're in state C or we're in state E. Otherwise, it's going to be a 0. That's all I really care about. And then how do I move from one state to another? So looking at this, here's my reset. Okay, it's asynchronous because it's outside this clock event. So it says if you see this reset line go low, then go to state A. So my first uh, input to the state machine in my test bench should be reset going low, and then I can leave it high for the rest of the simulation. So we start out in A, but then here we're looking for a positive transition on the clock. I don't know why it was positive. That was probably an arbitrary decision. It could have been a negative edge of the clock. This one's positive edge. It could also say in here if rising edge, right? You guys have had used, is it rising edge and falling? Rising edge and falling edge? Okay, you could use that in here too. All right, so if it's not reset, then we're going to check the clock. For the case of this signal, which is a state type, if it's state A, we're going to check to see if W is a 0, and then if it is, we're going to go to B. Well, that's right what we have here. If we're in state A and W is a 0, we're going to go to B. If we're in state A, the only other place it could go is D, and that would be if W was a 1. So we don't have to ask if W is a 1. All we have to do is say if it's not 0, we know it's a 1. And then we end that if. Again, I didn't do this the way I normally did. I tried to squish this whole program so it would fit on one page. Then this section is for state B. When we're in B, if W is 0, we go to C, else we go to D. So that's what we got here. If W is 0, go to C, or Y is assigned state C. Otherwise, Y is defined or assigned state D. When we're in C, if W is a 0, then we go and stay in C. Now this is the first time that we've got two zeros in a row. Now we've got a third 0 in a row. So our output's 1. We stay in C, and it's just going to keep going for a 1 there. If it's not a 0, we go to state D. But that's where we've been going every time that we had one input of 1. And then finally, if we're in D, If W is 0, we go to B. That's what this says. Else we go to E, which is down here. So to me, either one of these, using the state diagram or using the state table, either one, you can go straight to the VHDL with that. You might have to include a couple of standard variable things or variable types up here, signal types up here. We got a process. I decided to use a process and use reset and clock. I could have said begin or process begin and then said if reset equals 0, then we're in A, end if, and then here said wait until rising edge of the clock, right? We could have done a lot of different things here. Okay, this is what it was synthesized to. Notice it's showing 3 different C flip-flops in this one lookup table. Again, I did this. I'm going to soon change these over to VHDL test benches. But here it's no real big deal. I have a clock. The period on the clock is, what is that? 2, 3, 4. That's 1, 2, 3, 4, 7. Ooh, I'm not sure exactly what they are, but it's in there. And then on rising edges is where I've got W. Here I've got it high, here I got low, then high, then low twice. So I'm gonna, when we had this this kind of test bench, what was ever on this yellow line was ignored. We would only put this in there to say this is what I expected, but we never it never did anything with it. So I expected, because there were 2 zeros, I would get a pulse out of Z. Okay, and here I see 2 1s, I expect a pulse out. Okay, let's see what we get. Well, here were the simulated results, and it actually worked out just the way I wanted. We had a low, and then we had W was high, W was low, W was high, W was low. All those times the output Z. But then here we've got a second W is 0. That's a situation when we go high on the output. We get an output pulse of 1 for that occurrence. Then it went high again. What I should have done here, and I do a lot of times that I did not do in this VHDL, I also include the outputs of the flip-flops. And that way, when I get in here, I can see what state I'm actually in. This doesn't let me know very well what state I'm in, right? I can only guess what state I'm in. Okay. Then we implement the design. So we did that. Now we're going to do it with, go back to the state table, and we know that we've got 3 bits, or need at least 3 bits. So I'm going to need this. And look, I've done this a whole lot different than I normally would. I've got 0, then 4, then 6, then 5, then 7. And what I was trying to do here was say, let's keep, let's only change 1 bit at a time if we can. So 0, and then 1, 0, 0, and then here we changed 1. And then here I changed 2. I couldn't get away from it. And then here I changed 1. Okay. I chose the flip-flops. I used D again. And again, this is what I came up with. And each one of these, W was 1. I'm sorry, D2 was a 1. That's actually going to save our design quite a bit. Here, I've got D1 is a 0. Here, I've got that we got a 1 when W is low, so not W. And then here we've got, I'm sorry, we got a 1 here, and that's when W is low, so not W. Here we got a 1 when W is high, and here we got a 1 when W is high. In all these cases, we've got 1s when W is high. Okay, and our output again is associated back with the flip-flop. So we start with D flip-flops. We've got 3 state variables, so this is a 2 by 1, I'm sorry, 2 by 4 type of K-map. It looks like I went ahead and figured out, here's D1. I don't know what D2 was always 1, so D2 equals a 1. For here, we had D1 was just, what did we have? I didn't have it yet. I figured that out to be this, which was that expression. And then D2, I figured out was also, okay, that was a 1. D0 was just W, since these were always zeros or don't care. Okay, so here's W, or I'm sorry, D1. So that last one, that was the only one that needed a Carnot map, or at least I needed a Carnot map. So this is what my circuit looked like. I had an input of W to this flip-flop, had this as the input to D1, and here I showed a 1 as the input to D2. I'm going to change that in a minute. So here I've got 1 to D2. Well, what happens to Q if I've got D tied high all the time? It's always 1. These are going into this one, and then we got this down here. So we found out that our output could just be D1. So I said, okay, the output from flip-flop D1, there's Z. Since this is always going to be a 1, I took it out and said this is what my design was, and I just let the input or the output of actually I didn't care what was going on with that last flip-flop. We weren't working with the outputs of the flip-flops, so we just cared when Z went high. Okay, now let's look at and I'm still working on a presentation I can put out here about the different test benches, and I'm probably going to have to go back and put some of those test benches in here, and get rid of some of those older ones. We did the sequence detector. We've done this one, so we need to go look at the vending machine, and this one's going to take more than one, but because of the way I do the traffic signal, most people have chosen the vending machine part of for their program, or for their project 5. Okay, so here I've got a vending machine. I want to design it, state diagram, design a state table, write the code for VHDL, and then simulate it. We're not going to worry about implementing the design with all these components. And actually, on the last lab, I think I've already told you this, on the next lab that we're working with tomorrow, instead of building all those flip-flops, what we'll probably do is download those circuits to the Spartan 3 board and then we'll go ahead and I'll show you how to hook those some outputs up to the scope so you can get your signals off of there. Okay, here's our machine. Here's a design description. It takes quarters only. I'm going to show you how in your project 5 and again, most people take this one because it's better defined, or take this one because it's better defined. This one accepts nickels and dimes and quarters. So we have an input of a quarter, input of a dime, or input of a nickel. This one is going to take quarters only. So there's a difference between this and your actual project. This one also, last year, they talked to me into, how did we do this? Sorry. Here, they talked me into, if they had a coin return, it would just drop all the coins, but and it would do the same thing for giving change, but coin return could, yes, drop all the coins. That's the way these things work. But in giving change, it couldn't just drop all the coins. They talked me into letting them do that last year, and it simplified their design so much. It was like, why do it? So we're not doing that. If you buy something that's gum, and gum is 25 cents, and you put 35 cents in the machine, then you got to figure out what the change is and give that back. Okay. I still think this is the easier one to do. Okay. In this machine, we can get water for 75 cents, cola for 50 cents, and a good cheap beer for 50 cents. 50 cents a beer is about as cheap as I've ever seen them, right? If what? Do they even sell cigarettes anywhere anymore? Actually, I heard that CVC or Z, is it CVS was going to quit selling them because they're a pharmacy and they're there for health. So why would they sell something that would make you unhealthy? Because they're a pharmacy that's always sold cigarettes. I used to be a smoker. I think it's appalling what our country is allowing uh, people to do to smokers. It, you should be able to smoke if you want to, without everybody in the world looking at you like you're a PI or what. I do. I think it's terrible the way that people are treated because they smoke. Well, on this, on Central Piedmont's campus, for instance, no smoking anywhere on the campus. At a lot of hospitals, no smoking anywhere on their campus. On this campus, we're this close. We're this close. They've got, and I see people doing this every day, and I'm thinking they might be messing this up for themselves, but they've put designated smoking areas on campus. I don't like that idea either. But when everybody's ignoring this designated smoking area and coming over here or up in front of the doors, then eventually the people that make the decisions are going to say no smoking at all. And they're still going to smoke cigarettes. I'm sorry? I said they're still going to smoke cigarettes wherever they get smoked. And they still are. and it won't be long, and the campus police will be handing out tickets for that. And I don't like it. I'm not. I'm just saying that that's what we're looks like what we're heading for. For the first time, I'm seeing those signs outside that say, what is it? Don't walk and smoke or something like that. Because they want you in one place. They 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 want your butt in the designated smoking area in order to smoke. So, all right. If any of you guys smoke and you're being treated poorly, I'm sorry. I hate that for you. I didn't quit because uh, I was being treated crappy. I quit because my wife was going to kill me if I didn't. It didn't make sense to me because she wanted me to quit because she didn't want me to die. But she was going to kill me if well, that's the way it goes, right? And I had said something about I will quit when I finish my PhD. And I finished the damn PhD. Like I said, it was too easy. And then I had to quit. That was a lot harder. Okay, back to our machine. We got water, cola, or cheap beer. If we could have cheap cigarettes in here, we could really make some money. Uh, okay. The machine does have a coin return. Uh, this is very important, and it is exactly like uh, the project itself. That are we still talking about cigarettes? Well, no. In Japan, you can actually buy beer in a vending machine. You can't. I was making this up. I swear to God, I was there for 2 years. You can literally get beer in a vending machine. Okay, well, then I was futuristic. I didn't know they. That will never ever happen here, unless they're gonna make it so you scan your ID and then you can buy beer. Oh, that's true. And that wouldn't work either because they're like, yeah, let me borrow your ID. Because the next your buddy could be old enough to buy, and I'll buy a case. Okay, your project, if you should choose to do this one, also says only one input may be active at a time. That's extremely important to keeping this particular state machine simpler. If you could have a whole bunch of inputs active at one time, uh, that would make it a lot harder. But think the way a vending machine upstairs would work. Uh, do they can more than one button be active at a time? No. It ignores everything but one, right? So it's just like them. Only one can be active at a time. I've seen people try to do things like put in all the money and then try to hit the coin return and cola at the same time to see if they can get their money back while they get their Coke, and it doesn't work. I do know somebody that knows the code for the vending machine guys that come around, and he knows the code to get a free Coke. I've seen him do it several times. All you have to do is just laminate a dollar bill, put it in, have a string pull it to it, and just pull it out. Okay. But our machine is going to be able to check and see if you've done that. Just so you can add like a hole so you can connect the string to it. You put it in and then just instantly pull it out and it'll read it like, okay, thank you. And then it thinks it's putting it in there and then you just jerk it out and it's a dollar. Okay, we're learning all kinds of things today. Imagine, you didn't know you would learn this much coming to class today, did you? Okay, so this is important too. A product can be dispensed in one clock cycle. So we get, a pulse that should turn on some kind of something uh, that would say, okay, dispense a cola or dispense a beer. Sometimes I think it would take more than one clock cycle, but there you go. If more than 75 cents, more than the most expensive item is inserted, the money is automatically returned. What I mean by that is that extra quarter is automatically returned. On your project, it'll say down here that if that correct change must be provided for any purchase if more than 35 cents, and that's because the most expensive item is 35 cents. So if any more than 35 cents is ever entered in the machine, uh, then it refunds the excess money. So if you've got 25 cents in and you put in another 25 cents, it should immediately go and give you 15 cents back, right? And then you're stuck in a state where you've got 35 cents. And this one, by the way, your states should be by the amount of money in the machine. And you should go up from one state to the next by nickels, because you can put nickels in as the smallest. So every time you drop a nickel in, you went from zero in the machine to 5 cents in the machine, then to 10 cents in the machine, 15, all the way up to the highest possible value you could get, which is somebody could put in 2 dimes. Ooh, that's tricky. 2 dimes and have 20 cents, and then drop in a quarter, and maybe even 3 dimes and drop in a quarter, and they end up with 55 cents in the machine. So a lot of change has got to come back. There's a tricky one in this, I'll tell you right now. If you'll get to a point where either 2 dimes must be dispensed or 2 nickels must be dispensed. And it says down here basically that only one product, and that includes, somewhere in here it should say it more precisely, but one product or one coin can be dispensed in any cycle. So you cannot return 2 dimes or 2 nickels at one time. So you'll have to figure out, how am I going to do something like that? All right. We keep going. If there's no active state, the state machine just stays in the current state. And our outputs are coin return, water out, cola out, beer out, or quarter out. So in other words, this one is simpler, but it is an awful lot like the first one in Project 5. And so you have a lot of examples here to go by. Okay, so we got that. Here's the state diagram I came up with. Okay. If I can hear you guys talking, I know other people in the room can hear it, because I can't hear shit. Okay, that's better. I can't hear anything now. That doesn't mean people aren't talking. It just means I can't hear it. The machine takes quarters only, so each one of these I've got quarters in, or once I have enough money, I've got like C, where it could say CI, where cola is in, or something like that. Okay, so the machine can dispense these. The machine has a coin return, only but one button active at a time. These are all the things we said before. So my first state, I'm asking, will this actual state machine diagram, this state diagram, work? If nothing's happened, we stay in A. That part will work. Here, if we put 1/4 in, then we go to state B that has 1/4, but we can't get anything yet. So we should ignore it when somebody presses something like, uh, you know, some dumbass up in the machine keeps trying to press cola and they've only put a quarter in and they finally go, oh, duh, I've only put a quarter in. Hopefully, or somebody has to come by and tell them that they've only got a quarter in. Then you get a coin return. You could possibly get a coin return input right here. And again, I can still hear you guys talking back there. So really, hold it down or quit or something so that everybody else can hear. The coin return goes to this where it says coin return out and all the coins come out and we go back to A. The next one is D. We got another quarter in. So from B, we can either put a quarter in or we can hit coin return out. One or the other. We can't do both. So now we can do nothing and stay in B, hit the coin return, and all the coins go out, or insert another quarter and wait. Okay, if we're in state D, then we've got 50 cents in the machine, and we can do something now. So we can do nothing and just sit there. We can, and we don't have to show it. We just say there's no inputs, we stay there. We can hit the coin return and go to state C, return the money, and then go back to state A. There's that, or at least one unconditional transition. We could select a cola at this point because we got 50 cents in the machine and go to state E, output the cola, and then we go back to state A because we've output the cola, we have no money in the machine again. We can select beer, which goes to state F and outputs a beer. That's what this signal is here, BO, is outputs a beer and then automatically goes back to state A because there's no money in the machine. Or we can sit here in G and wait because we could also insert one more quarter. If we get to G and we've inserted 75 cents now, we can do only a couple of things. Well, we can do a whole lot of things. We could insert another quarter, but that quarter should just be returned and we go back to G. So we can stay here, but every time we put a quarter in, it's got to drop out. We could select water, get a water out, and go back to state A. We could, there's nothing wrong with having 75 cents in the machine thinking water and then deciding, well, no, I think I'd rather have a beer, or no, I'd rather have a cola. So we've just got 75 cents in the machine. So if I choose cola, it should output a quarter. And look, there's a state all by itself where it outputs a quarter, and then it goes to cola out, and then back to A. So this is real similar to that thing I was telling you about earlier where we have 2 dimes or 2 nickels that it could output. That there we got something where we got to output 2 things at one time, and we're actually going to have to take 2 cycles to do that. If we're in G and we say beer, we'll go down to quarter out and then beer out. Now, I tried it a different way at first. I said, well, why don't I go right over here to beer out? But there was no way of saying quarter out here. Okay, there was, because if I said quarter out there, then if every time I hit a beer, I'd get another quarter out. So that wasn't right. So on both of these, I have to put the quarter out first and then go to the state that outputs either the cola or outputs the beer. So I think this is a good state diagram. I think everything will work. So now the thing is to implement it in a VHDL file and then test it and see if it works. Okay. This is very similar to this particular machine, but think about it. If you put these amount of money, then you've got you could put in nickels for all this, but you could put in other combinations of money. The highest amount of money that you can get to is putting in 3 dimes. That's 30 cents, and then dropping in a quarter, and that's 55 cents. What are you going to do if you drop in 55 cents? Well, it says you got to give back some of the money. Well, if you got 55 and 35 is the most you have, you either got to return 2 dimes, can't happen in one cycle, or you can return a dime and then return 2 nickels, and the 2 nickels can't happen in one cycle. So this is the condition which is going to be a little, it's going to be the one that is you're going to have to work through. Okay, the otherwise the rest of them's fairly easy. Okay, so this is a lot like that. It should be good to go by. Okay, so we devise a state table. So we've got these possible inputs. Imagine what they would be for that other one. Here we got coin return as an input, quarter in as an input, cola in as an input, beer in as an input, and W in as water as an input. It's a lot of inputs. But on state A, we found all we could do, state A, there's really nothing you could do except for put a quarter in. So we can ignore all these other inputs. All we can do is put a quarter in. And notice each time it gets a little bigger, right? When we're in state B, we can either put a quarter in or we could hit coin return. If we put 2 quarters in, then we're going to go to this state that happens to be 50 cents. If we've got, if we hit coin return, we're going to go simply, that says next state is C. Okay, and C is the one where it doesn't matter what all the any inputs are, it's ignoring them all. It's outputting, here's all our outputs, we got plenty of outputs. It's outputting the coin return and then going back to state A. Now this is a weird way to do the outputs. I've never done it before. I've had either a 1 or a 0 there. But this is saying 1/0. What I'm trying to show here is we're going to have a single pulse of 1 out, and then it's going to go back to 0 by itself. So we don't say 1 and stay there, but we could, since no matter what, on any one of these that we've got an output, or at least this one, these two, and this one, we go back to state A. We could say that in state C, the output's a 1, state E, this one's a 1, that one's a 1, state H, this one's a 1, and then when it goes back to state A, that the output's a 0 for all of them. We could do that. There are several ways we could do it. I just think this happens to be easier, and I'll show you the VHDL that's a little different than what we've done before that allows you to do this. Okay, allows you to output a 1 for a certain amount of time and then go back to 0. Okay, so we've got all those. We're not going to fool around with the flip-flops, are we? So we got this entity where we've got a clock input, a reset input, coin return, quarter, cola, beer, water. We got outputs of coin return out, quarter, cola, beer, and water. And then we got Q that's going to tell us what states we're in, and it's from 2 down to 0. So those are our state variables here. There's got to be 3 of them. Okay, here's the architecture for it, and I go right off of here. If we reset and I put everything back to 0, and I put us in state A, we do the typical new type of variable, which is a state type, and we let signal Y be a state type. So here, if we're in case A, then Q will go to this. Now, this may not work. I think it did work for me, but this was an earlier version of Xilinx. Here, you might have to have a signal of QX is equal to a logic vector 2 down to 0, and then put QX, or Q equals, sorry, Q is assigned QX down here. You may have to do that. On another one, I got an error when I had when A, then Q is assigned this. It didn't like that at all. So these are just 2 places I've had errors before that you might want to watch out for in this version that you're using. This was done with version 7. You're using version 14 point something, aren't you? I think this one it was 17 or 7.1. Anyway, if I'm in state B, this one says, well, I can look for, then this is my code. Q is 001, all the variables. If I hit a coin return, then I'm going to go to C. Else, if I hit a quarter in, then I was going to go to D, and then end if. So that's all I've said. For C, I've got if I'm in C, the Q is going to be 010. That shows it right there. It doesn't look at any other inputs, but it does say CR0, coin return out, is assigned a 1 after 0 nanoseconds. So immediately it's assigned a 1, comma, a 0 then after 200 nanoseconds. So it's putting out a 200 nanosecond pulse, okay, that should be enough to implement some, or to turn on some kind of actuator that would dispense the coin return. But that's an interesting little line, and we've got several of them down here throughout this one that is nice. It allows you to output a pulse. Output the 1 after 0 nanoseconds, and then 0 after 200. Okay, then D, we said that our state variables were this, and so on and so forth. So you guys can go back and look at any of this if you want to. Here's my state table, so, or my simulation. If I were writing this in VHDL, I would allow the clock to just run. I would make reset low for just a short period of time and then make it high. And then I would start putting in some quarters and seeing if I got stuff out. Now on yours, you've got so many things, you're probably going to have several different VHDL test benches, because you could be putting nickel after nickel after nickel until you got up to 40 cents. And that's as high as you can go. You can get up to 55 cents. There's on that one, there are so many possible uh, combinations that you're going to end up probably with 5 at least, maybe more test benches. And I would get that engineering paper and draw it out like this first, okay? And draw it out and say, this is what I want. Decide how long uh, each one of your little squares on that paper is going to be. Is it going to be 50 nanoseconds or 100 nanoseconds or what? But figure it out here like this, and then input it that way in your VHDL test bench. Here, and it's similar to this in ISIM, if you hit this, it opens up our queue to show us exactly which state we're in, which is nice. So here's my output. And I like this too. ISIM does this also. It says we're in state 0. Well, which one was that? Let me go back a few. State 0 was A. It tells us, oops, damn, sorry. It tells us we're in state A. 001 is B. This one, I believe, is C. Let's go back and just look at those for a minute. 0, 1, 2, 3, 4, 5, 6, and 7. So we should be able to tell by these exactly what state we're in. So here it shows we're in state A. We put in 1 quarter. We went to state B. We put in another quarter. We went to state C. And we had an input that was beer in. And then we had an output that was beer out. And we went back to state 0. And if you don't like it this way, you can open this up and you can see I'm in state 0, I'm in state 1, I'm in state 3, and I'm in state 5, and then I'm in state 0 again. However you like to do it. It would also be very nice if all the inputs were together and all the outputs were together, or you might say beer in, beer out together, cola in, cola out together, water in, water out together. However you want to do it. These can also be changed to different colors. I would highly recommend that to make it easier for you to write and easier for me to read. Okay? So if you could say the quarter out, the red line, I'd know exactly which one you're talking about, and it would be easier for you to write about it instead of saying the third one down or something like that. You'll have more inputs than this. When you got that, very difficult to explain what the diagram is. I would also take this into Paint or take this into PowerPoint and draw little pulses and put in the time periods so you can tell me at T1 this is what's going on, at T2 this is what's going on, because you want to make it clear to me. I'm not going to spend a whole lot of time going into these. Okay, I'm not going to spend a lot of time. I can't. So you've got to make it as clear as possible, or I'm going to go, I don't know what the hell it is I'm looking at. Okay, here's a second simulation I did. I put in a whole bunch of quarters. I wanted to see if I'd get a bunch of quarters out. And then I selected a beer, and then I put in a bunch of quarters, and I selected a cola. And then with no money in, I hit water, and then hit carriage return. I wanted to see what would happen. Colors. I finally learned to do colors. Here shows that there was a quarter in, a quarter in, a quarter in, a quarter in. So it shows I went to 0 to 1 to 3. And then this one was whatever state that was. And I just stayed there. And the output started happening quarter out. stayed there in that state, quarter out, uh, then another quarter out, and finally uh, this was shown, which was beer in, and I got a signal beer out, and then that took me at the end of that back to 0. These aren't exactly lined up, are they? But as long as it functions, that's what I care about. See how I did this? Red. 5 quarters in, after 3, they start being returned. And I've got little arrows showing that's what's going on here. Okay. Here, I've got blue. I'm talking about this line. I buy a beer, another quarter is returned, and then the beer is dispensed. And that's beer is the blue. Then I've got more quarters are coming in. After 3, they start being returned. That shows that. And then I've got in yellow, a cola is purchased and a quarter is returned up here. And then the cola is dispensed. And then here, I finally get down to no quarters are in the machine, but I try to buy water and nothing happens. And then I hit coin return, but nothing happens. So this machine was really working the way it was supposed to work. Okay. Now this is very, very, very similar. This one here. Oops. When you come up to this vending machine, it is very similar to this first one in your project. Okay, so this is all about the vending machine. This is all about how the project's supposed to go and what you have to turn in. And then you've also got a choice of a traffic design. So you can choose either one. Next time I'm going to show you the traffic controller I did, and you don't have to do it the way I did, but what I did was come up with 3 or 4 different circuits. Okay, and remember back in one of the labs, I know the guys in DE didn't do this, but you can follow along with what I did. Where you created a part, I created some parts. And then I put it in a schematic and had to connect it all together with a schematic. And I believe, because of the way I've done this one, that's why so many people choose vending machine. I believe. I may be wrong. And then I'll show you this timing analysis, okay? And I'll try to finish that particular presentation that shows more about, or at least the one I've got right now, the way it is, it shows a lot about putting in VHDL test benches for state machines, okay? That's what it's showing you. All right, I will see some of you tomorrow and some of you in a few minutes.